Hello, this is the last section of chapter 14. It's 14.8 Logarithms and Nonlinear Data. We've seen as we've gone through this chapter that logarithms have helped us to find x, and where x has been the exponent. This is now going to show us another way we can use logs, and I find this quite fascinating. When you do science, you often have a graph, and the graph that you get is maybe has a number of points on it like this. This is perhaps not the best example you'll ever see. And you then draw a line of best fit, and you would then use that perhaps to draw conclusions about what might happen within the range of the data. Now that's all well and good when you have correlation that's linear. Now life isn't always like that, and I can remember in my physics lessons when I was doing A-level in particular, I might get a graph that was a little bit more like this. I'm going to be honest, I can't remember what experiment I was doing, and the problem is you can see that this wasn't linear and that really I needed to sketch a curve, and that gets quite problematic when you're doing a line of best fit and so on. So what we can do is use our logarithms to take nonlinear data, which would be here, and by using logarithms we can make that data linear, and by taking logs of different parts of the expression, and then we can end up with a linear data that we can plot, and that way we can draw our line best fit and actually starts making what would be hypothesis or about the data, and also we may go on and come up with conclusions about what might happen within that data. So this you might see in your science. I'm not sure whether it's still done at A-level. However, it would definitely be used as you move on and do science at university. If I look here, there are two ways that I might see an expression written, and I want you to notice the difference here. X and Y are my variables, and the other letters there are constants, but you don't know what they are. So just getting that in your head, as X varies, Y will vary, but A and N in the first expression, they are constant values which you don't know. So they could be 7, they could be 94, they could be 2.1, but A and N, they are going to have different values, but they will be constant, those values, as X and Y vary. So if I come over here again, X and Y will vary, so X will go up and Y will alter because of that, but the values for A and B will remain constant, but again we don't know what they are. And what we're going to look at now is where the X is. So here the X is the base, and here the X is the exponent, and I want you to see that because these are different cases. And I'm just going to write under here A and N are constants. So that value doesn't change, and A and B are constants. So their values don't change again, but we don't know what they are. Now for the example on the right hand side, let's take logs of both sides, and I'm going to write log of y equals the log of ax to the power n. Now I need to use my log rules, and I can write the log of y is equal to the log of a plus the log of x to the power n. And if we remember here, what we're actually using is the multiplication law of logs. Now when I go to here, I now can use the power law as well. So log of y equals log of a plus n log of x. Now I just want to, this bit here is a bit that varies, and this bit here is a bit that varies. So x is going to have different values, so log x will have different values. Y will have different values, so log y will have a different value. But log, as a is a constant, it's always the same value. The log of a will always be the same value. And n is a constant, so we are always multiplying by the same amount. Now the significance of this is if I write now y equals mx add c, then I can say this would be log y equals n log x add log a. So what I'm doing is I'm comparing this written in a slightly different order with y equals mx plus c. So y, what I would plot on my y-axis would be log y. What I would plot on my x-axis would be log x. The gradient of that line, so having plotted the log of y by the log of x, the gradient of that line would be n, and I'd be able to work out what n is. So the gradient would be n, and the intercept on the y-axis would be the, would be the log a. So if I wanted to find a, I would have to find the intercept, and I would have to do the inverse of a log, which if I was using the natural log, remember, I would then be doing e, okay, using e to the power. So we will go through one of these examples, but what I want you to understand from this really is we have logged both sides. We've then used our log rules to get it in this format, and then I have compared it with y equals mx plus c. And the thing that we're seeing from this is that m is equal to the log, let me erase that, is equal to n, and c is equal to the log of a. And so if I find the gradient, I know what n is. If I find my intercept, and assuming I'm using log to the base e, I haven't said actually, it's though an assumption that it would be base 10, so I could do 10 to the c, and that would be equal to a. And if I did the natural log, then what I'd be doing there is doing e to the power of c, and remember that's the y-intercept equals a. As I've said, we will do an example, and it will make a little bit more sense then. Right, let's look at this one. And again, to start with, let's take logs of both sides. Can I suggest you pause the video now, and can you write the next stages? Could you get down to this point here maybe? Could you do that on your own? Because it's a good test of your skills. So press pause, have a go at writing that down, press play when you've done it. Okay, so let's have a go now. And keeping going, I would get... There we go. So just going over this, multiplication of law of logs here has let me split a and b to the power x. Notice it's only b to the power of x, so it goes there. Be careful with that so that you know where the x should end up. Then, having used the multiplication law, I can use my power law and I can multiply by my x. Now, I want you to compare this to y equals mx plus c and write it underneath. Off you go. Have a go now. See if you can do that. So, what I'm hoping you've realised is that the y would be the log y mx. So this actually would be x log b. Now, the gradient here is going to be the log of b, and then this would be the log of a. So when I am comparing, I would do m equals log of b. I would do here that c is equal to the log of a. And what two things am I plotting against each other? So I would plot the log of y against x. And here, remember, I would plot the log of y against the log of x. So can you see the clear difference between what you need to plot against each other? So this is the example from the book. I've actually taken this from Dr. Frost. Thank you to Dr. Frost, where he's kindly typed it back out. The question is saying the table below gives the rank and population of the UK's largest cities and districts. London is number one, but has been excluded as an outlier. The relationship between the rank and population can be modelled by the formula P, which is your population, equals A, which we see here is a constant as well as n. So A R, the rank to the power n. And then it goes on to say this, which Dr. Frost is saying is wrong. But I'm going to actually say, well, I'm going to ignore that, and to work out what graph I'd draw, I would write out my function. Well, that's rather thick. Don't know why it's doing that. Let's just pull that back a bit thinner. So P equals A R to the n. So log of P equals the log of A R to the n. Using my log rules, and that would be the log of P equals the log of A plus n log R. Now, when I'm doing this, I need to work out what my two variables are. And remember, they are the P and the R. And both of those are logged. So when I'm actually going to draw my graph, I've got to draw a graph, and this graph will have along the bottom log R, and this would be log P. And the reason I know that is I'm going to compare this to y equals mx plus c, and this here is my y, and this here is my x, and when I draw out my graph, I'm going to find the gradient, and my gradient will be equivalent to n, and my intercept will be equivalent to log of a. And so what it asked you then to do is plot a graph of log a against log p, and quite rightly so, he said it should be log p against log r. Anyway, whatever everyone is saying in here and the confusion, the key bit is if you write this out here and then you compare, you will know that log r is on the x-axis and log p is on the y-axis. So the first stage of this question is for you to draw out a new table and to find the log of r for each of those and the log of p for each of those. And that's what you need to do to start with. So what I've done now is I've remembering that the y-axis is log p, and from my set of values I have taken the log, and when I've used log, I'm using log on the calculator, so that, if you remember, is base 10. So I've done the log of 1 million, which is 6, which is right because 10 to the power 6 is 1 million, so you would expect 6. And then I type in log of 730,000 and so on, filled in all of those, and then the rank are, I've logged 2, 3, 4, 5, 6 and written those values in there. And now I plot them against each other, and this is where you see the magic happen. This here is an exponential graph. You know that's a curve. So this here is a curve. When you plot these on some graph paper, you're going to get a straight line. And that's really going to help you when you've got science data and you're trying to find out what A and N might be. So actually this is another wonderful bit about logs that I just think's wow. And I hope you think it's wow too. So you do need some graph paper now to plot these, or you could go on to GeoGebra and you could plot those on GeoGebra. You do need to go away and plot them. Off you go, have some fun, plot away, and then come back to see how the A and the N work. So I've drawn a sketch of hopefully the graph that you will have ended up with. Your values are likely to be different to mine, and that's the examiner's not going to expect you to get exactly the same results if they get you to plot them. Quite often though, the examiner might give you the graph, but what he might do is give you a graph. He might give you this expression. He might give you this graph, and then he might say use the graph to find A and N, but not give you a clue of how. And it would be up to you to realise you need to do this and then work out how to use the intercept and the gradient. So from this, I've also put on some key values. So this is a point I've chosen on my graph just here, and I've chosen this point here, and I've drawn my triangle to help me find the gradient. Okay, so where can I go with this? Well, first of all, I know that C is equal to 6.2. And if I go back to here, I know that my C is log A. So 6.2 is equal to log A. Now remember, my base is 10. So from that, I can say that A must equal 10 to the power 6.2 because 10 is my base and 6.2 is the exponent, because you remember that's your base, 10 in there, and because you're using the calculator log, that's what it means. So it's 10 and this is your exponent, 6.2, and you would type that into your calculator, and I'd write the answer to two significant figures, and so you'd get that A is equal to 1,600,000, and there's our value for A, which is brilliant. We've worked it out. Now we want to go on And the other thing we need to find is n. And n, if you remember, here's where n is there. N is our gradient. So to find the gradient, which remember is equal to n, we're going to do change in y over change in x. And again, I keep saying your answers will be slightly different. That's not really a big problem. Type that into your calculator and you'd end up with negative 0.67. And that's for n. Just want to check back if I got all of that correct. Use your graph to estimate the values of a and n to two significant figures. Yes, I have. So just a quick recap on that. First of all, take your expression, which is an exponential, take logs of both sides, rewrite it, and then compare it to y equals mx plus c, and understand what is your what going on the y-axis and what's going on the x-axis, and then it can help you to write those in there. Sometimes they will be the log of both of them and sometimes they won't. And it's only by doing this process you understand what you need to plot to get a straight line. Because remember, all of this is so that we get a straight line. Because if we have our data very close together on a straight line, we can draw a line of best fit. And if we draw a line of best fit, we then can write an equation for the data. And what I would say to you is think about your statistics, because in statistics we do about regression and correlation, and this all could link to it as well. So then we plot those values on a graph. So here's our graph, and we've plotted our values. And now, because we've been asked to find a and n is our gradient and a is linked to our intercept, we find our gradient and we find our intercept, and then we say, well, c was equal to log a, so I have to manipulate to find a, but n was just n, n was just the gradient, and we've worked it out. Okay, let's do our next example. Now for our next example, there was a little graph that I've missed off here. So I'm just going to quickly draw that in. This is t, and this here is log of p, and it's a positive gradient and an intercept at 2. Now let's read that question and understand what we're being asked to do. So the graph represents the growth of population of bacteria. They do like bacteria, locusts and rabbits, all of their favourite things, p over t hours. The graph has a gradient of 0.6, I think that's going to be important, and meets the vertical axis at 0.2. A scientist suggests that the growth can be modelled by the equation p equals ab to the power t, where a, b are constants to be found. Write down an equation for the line. So I can look at this to help me find an equation of the line, and remember that y equals mx plus c. So what is on my y-axis? Well, that's log p. What is my gradient? I know that from my question. It's 0.6. What's on my x-axis? It is t. And what is the intercept? It is 2. There we go. That's it done. Brilliant. No problems at all. B. Using your answer to part A or otherwise, find the values of A and B, giving them to three significant figures where necessary. Now there are two ways of doing this. So I'm going to show you both ways because I think there's a case of understanding how both ways fit together. So remember, we are trying to link this, and I'm going to write this down here because when I move up we won't see it. This was the original. Now I'm going to divide my page and do method 1 and method 2. So here we go. Now, no method is any better than the other, but I just know that different people think in different ways, and both methods will get you there. So method 1, I'm just going to look at this on the left-hand side, and I'm going to say, okay, I've got log p equals 0.6t add 2. So because I want to do the inverse function and get rid of my log, I'm going to write p equals 10 to the power of 0.6t add 2. All of that is a power. Now, if you remember, when powers are adding, what they're actually doing is multiplying. So that would be the same as 10 to the 0.6t times 10 to the power 2. Just remember that x squared times x cubed is x to the 2 add 3, which is x to the 5. And it's that rule that if your base is the same, so these bases are the same, then when they're multiplying you can add the indices, and we're just going backwards from that. So this would be p equals 10 to the 0.6t multiplied by 100. Okay, so going on a stage from there, I could write that this is p equals 10 to the 0.6 to the power t multiplied by 100, because if you remember, there's another power rule which says that if you've got a squared all cubed, that is the same as a to the 6. So you multiply the powers. So what we've done is said, well, these powers are multiplying, so that's the same as 10 to the 0.6 all to the t. Now I can do a bit of comparison with what I originally had, and I can see that from this, if I write it in a slightly different order, that my 100 is my A, and that T is actually not great being just down there. It should be a little bit higher, shouldn't it? It should be up here. And actually, there's a case to say that this, I've put my bracket there in the wrong place. That's better. I can then also say that B must equal 10 to the 0.6, which is 3.98 to 3 significant figures. So what I've done is I've compared this and said, well, A times B to the T, well, that's A times B to the power T. So A times B to the power T, so that's B and that's A. Now the second way of doing this, you may not prefer, so I'm going to do this on the right hand side, and I'm going to take the function here and rewrite it in terms of logs and then do my comparing with this. So this method rearranged it into this format and then did the comparing. Here I'm going to take this one, put it into this format and then do the comparing. So starting with p equals ab to the power t, I'm going to take logs of both sides, so log of p equals the log of ab to the power t. So log of p is equal to the log of a plus the log of b to the power t. So the log of p equals the log of a plus t to the log of b. Now, doing my comparisons now. So that bit there is you doing your bit of log rules. So log of p the same. 0.6 is the same as log of a, if you notice, because there's the t, there's the t. No, that's not a t, that's an add. Can you see how my notation's really poor there? And I'm glad I've did that, because that's what students do and then get in a terrible muddle. And it's good when teachers do it. So it's log of a add, and that should be a nice curly t. That's better. So let's start again. 0.6t is linked actually to that, if you look. So the 2 is the same as that, and I could write it underneath to help me. So this would be the log of p equals 2 add 0.6t. Now, what that means is the log of a equals 2. Now remember, the base for this log is 10, so I can say that a is equal to 10 squared, which is 100, which we worked out previously, and it matches, which is good. And we can also say, I'm just going to move it down a bit so we can do that comparison from here to here. We can also say that here that t and that t go together, so this log b is equal to 0.6. So log b is equal to 0.6, so b is equal to 10 to the 0.6, which is equal to 3.98. So it doesn't get you different answers, it's just different ways of seeing it. Neither route is any better than any other. I think this route shows a really good understanding of how to manipulate and go backwards and forwards. It's lovely. I think this, though, reinstalls your knowledge of your log rules, and it does the comparing the same. So if you do it that way and you get it, you get full marks. If you do it that way and you get it, you get full marks. Go whichever way works for you. Now, that answers part B. And then there's this last part, which is C, and it asks you to explain the meaning of constant A. Well, if we look, constant A, this here, is linked to the intercept here. Now, they like questions like this. They like to ask you to explain what something might be and link it back. These won't be big marks, so please don't worry about that. But this is the bit that, just work this through. This is where you're going to get that mark someone else isn't going to get. So what we know is A is linked with this point here. What can you tell me is going on at this point here? Well, time is equal to 0. So the answer for C is the value of A is the initial size of the population. And you do need to go back, and it's a population of bacteria, by the way. You do need to go back to here to see that, because when time equals 0, this would become P equals AB to the 0, because this A value we have already said from before, it won't move up and down for me now, there we go, is linked to the intercept. Okay, so we said this is linked to our intercept here. And Therefore, if it's linked to the intercept, A is linked to what happens initially at t equals 0. And coming back to here, when t equals 0, this is what happens, and anything to the power 0 is 1. So we can then write that p would equal a when t equals 0, which is where the value of a is the initial size of the population comes from. So it's linking together, just going through that again, that it's the intercept on the y-axis, which is when the variable that is on the x-axis equals 0. And because it's time and it's 0, we're then saying that when initially, because that's when time is equal to 0, thinking back to the words used in mechanics initially, that when it's initially, the population would equal A, and so it's the initial population. Okay, lots of practice needed on those. It's mainly the manipulation that they will test you on, not so much the graph drawing, but they could.